Okay, the spherical coordinates of a point are as follows. If we draw a vector from the origin to the point, that vector will have magnitude rho. So you can think of rho as the distance from the origin to our point. Just like r is the distance from the origin to the point where that point, where our original point projects to the xy plane. Rho is simply, we don't have to do any projection, rho is just distance from here to here. Okay. Now, the other coordinates, okay, we didn't have to project anything to get rho, it's just a direct distance. But the other coordinate will be the theta, same theta, so I've written it in purple as well as orange, the same theta that we used in the cylindrical coordinate system. Okay, so it's just, if we project this point down here, we get this vector. We don't have to really worry about r because that's not part of our, that's not one of our spherical coordinates, it's one of our rectangular, or our cylindrical coordinates. But we still have this projection and this vector, and then we're going to measure the angle theta down here in the xy plane, and that will be one of our spherical coordinates. Okay, so knowing theta and rho, that still doesn't tell us exactly where the point is, because now yeah, we've gotten our theta by projection, but we don't know, just, you know, this point could be anywhere above or below that projected point. Where it is depends then on this final angle phi, which is the angle from the z-axis to the vector from the origin out to our point, this vector here. Okay, so that's our last coordinate, our coordinate phi. So the coordinates are rho, theta, phi. Now, let's see how the rho, theta, phi coordinates relate to the cylindrical coordinates r, theta, and z. Okay, well, theta is the same in both systems. Okay, what about r? R is the length of this vector, which corresponds to this side of a right triangle that you see right here. Okay, well, phi is the angle here. This projection line is parallel to our z-axis. So this vector from here to here is a transversal of two parallel lines. Okay, line that intersects two parallel lines, and you have alternate interior angles here. So this angle is the same as this angle. So here's our angle phi. Now here's our right angle right here. So how does r relate to rho and phi and theta? Well, it doesn't depend on theta. Theta kind of depends on where this is, but the dimensions of this triangle, hypotenuse is rho, angle up here is phi, and r is the leg that's opposite that angle phi. So r must be rho sine phi. Very straightforward if you are conversant with right angle trig. So that should be obvious, and then it should be equally obvious that our z coordinate from cylindrical system is this leg of the triangle, which is the adjacent leg, the leg adjacent to the angle phi, so that z is rho cosine phi. Okay, so there's our comparison of the cylindrical and spherical system. Now if you try to go the other way from the cylindrical to the spherical coordinates, well, rho is just going to be r squared plus z squared, isn't it? Okay, and then you can ask yourself, well, theta is going to be the same. What's phi going to be? It's going to be an arctangent of z over r. And then you got to worry about, you know, whether z is above or below the axis. But that's going to work out just fine. One other thing about phi is Phi is the closest angle to the z-axis. So we would measure phi here for a point above the xy plane, such that phi is less than 90 degrees. We don't measure it from the negative part of the z-axis. And as a matter of fact, we always measure the angle from the positive z-axis, so that if a point is below the xy plane, phi is going to go past 90 degrees, but it's not going to go past 180 degrees. So the angle phi will always be between 0 and 180 degrees. Now, to get the x, y, and z coordinates, well, we've already got the relationships for the cylindrical coordinates, and we've got the relationship for the x, y, and z coordinates in terms of the cylindrical coordinates. X is r cosine theta. Okay? Well, r, and we can see it directly from this triangle, r is rho sine phi. So to get this side, we take r, which is rho sine phi, and multiply it by the cosine of theta, and we get rho sine phi cosine theta. Now formally we can just replace r with rho sine phi, but we also want to be able to see it in terms of this picture. And it's not difficult to see. We can see that this side of this hypotenuse of this triangle that we use down here in the xy plane is rho sine phi, so that this, which is going to be the hypotenuse times the cosine of theta, has to be rho sine phi cosine theta. And similarly, and I'll leave it to you to work this out, but it's very simple, that y is rho sine phi sine theta. And z is the same as it was here. Z is rho cosine phi. So I could have included that since I'm writing these in. Put these together, and this is our relationship, set of relationships between the XYZ system and the rho theta phi system.